Hello and welcome to G Fun Facts Online. Today we're diving deep into a silent global crisis. Imagine a condition that causes osteoporosis, but for the entire ocean. A change that's making the very water corrosive to the animals that live in it, dissolving the shells of some creatures while they're still alive. This isn't science fiction. It's called ocean acidification, and it's happening right now, driven by the carbon dioxide we release into the atmosphere. So, how is marine life facing this acid test? Let's find out. First, what's actually happening? For thousands of years, the ocean has been our planet's great protector, absorbing about a quarter of the carbon dioxide we produce. But we're now pumping out CO2 at a record pace, about 22 million tons every single day. The ocean simply can't keep up. The chemistry is straightforward. When CO2 dissolves in seawater, it forms carbonic acid. This weak acid then releases hydrogen ions. More hydrogen ions mean higher acidity and a lower pH. Since the Industrial Revolution, the ocean's surface pH has dropped from 8.2 to 8.1. That might sound tiny, but the pH scale is logarithmic. That 0.1 drop represents a staggering 30% increase in acidity. This rate of change is likely faster than anything the planet has seen in the last 55 million years. But it gets worse. This process triggers a second, equally dangerous effect. The building blocks that marine creatures use to build their shells and skeletons are called carbonate ions. The extra hydrogen ions in the water are stealing these carbonate ions, bonding with them and making them unavailable. So marine life is facing a two-pronged attack. The water is becoming more corrosive, and the essential materials they need to build their protective homes are disappearing. The most immediate victims are the organisms known as marine calcifiers, the builders of the sea. Let's start with the most famous, coral reefs. These vibrant, sprawling cities of the sea support an estimated 25% of all marine species. Corals build their intricate skeletons from a type of calcium carbonate. As carbonate ions become scarce, it takes much more energy for corals to build. Their growth slows down, their skeletons become weaker, less dense, and more easily eroded by waves. Under some scenarios, by 2050, over 90% of coral reefs could be in water so corrosive that they start to dissolve faster than they can grow. If these reef cities crumble, it triggers a catastrophic domino effect, wiping out the homes and food sources for thousands of fish and invertebrates. It's not just corals. This crisis is hitting our dinner plates. The global shellfish industry, worth hundreds of billions of dollars, is on the front lines. Between 2005 and 2009, oyster hatcheries in the U.S. Pacific Northwest saw billions of their baby oysters die. The cause? Highly acidic deep ocean water was being drawn into the hatcheries, literally dissolving the tiny, delicate shells of the larvae before they could even form. Adult oysters and mussels also struggle, growing smaller, weaker shells, making them more vulnerable to predators and less valuable at market. Then there's the unseen majority. Tiny swimming snails called pteropods, also known as sea butterflies, are a critical food source in polar oceans for everything from salmon to whales. Their fragile shells are already being observed dissolving in the corrosive waters of the Antarctic. If pteropod populations collapse, it's like pulling a major thread from the bottom of the food web. The entire fabric could unravel. But this isn't just a story about shells. The changing chemistry affects marine life in shocking and subtle ways. One of the most alarming discoveries is what it does to fish brains. Studies on clownfish larvae, think Nemo, are terrifying. When raised in water with CO2 levels predicted for the end of the century, they lose their ability to smell the difference between a predator and a safe space. In some cases, they actually become attracted to the smell of the animals that want to eat them. Their behavior becomes hyperactive and risky, straying farther from shelter. This is because the change in water chemistry messes with their internal acid-base balance, which in turn disrupts key brain functions. And it's not just fish. Every marine animal has to work harder to maintain its internal chemistry. This is a huge energy drain. Think of it as a universal tax on survival. That energy can't be used for growing, reproducing, or fighting off disease. For example, when brittle stars in acidic water need to regrow a lost arm, they lose muscle mass in their other arms to do it. Jumbo squids, which need huge amounts of oxygen for their high-speed pursuits, are predicted to have their activity levels cut by nearly half, dramatically shrinking their hunting grounds. Every creature, even if it survives, becomes weaker and more vulnerable. So, the ultimate question is, can marine life adapt? It's a race against time. Some organisms can acclimatize, and some populations might pass on resilience to their offspring. Evolution through natural selection is also possible, especially for species with huge populations and short lifespans, like phytoplankton. We've seen this in labs. A species of plankton grown for 500 generations in acidified water did evolve to partially restore its growth rate. And in the wild, at natural CO2 seeps, which are like windows into the future ocean, we find corals with genetic traits that help them survive. But there are huge limits. First, the speed of change is the real killer. We're pumping out CO2 10 times faster than the event that triggered the last major ocean acidification crisis, the Paleocene-Eocene thermal maximum 56 million years ago. That event caused a mass extinction. Today's animals have 10 times less time to adapt. Second, adaptation has costs. A copepod species that evolved to tolerate acidity lost its ability to cope with food shortages. An animal that adapts to acidity might be wiped out by rising temperatures. Marine life isn't just facing acidification. It's facing a triple threat of a warmer, more acidic, and less oxygenated ocean. These stressors combined are far deadlier than any one of them alone. The situation is dire, but not hopeless. The path forward requires a two-pronged approach. First, and most importantly, we have to treat the cause. The only true, long-term solution is to drastically cut global carbon dioxide emissions. This means a rapid transition away from fossil fuels. It's the ultimate fix. While we work on that, we also need to bolster the resilience of marine ecosystems. This means creating and expanding marine protected areas, which act as safe havens from other stressors like overfishing and pollution. It means restoring coastal ecosystems like mangroves and seagrass beds, which can absorb CO2 and locally buffer the water's pH, creating small pockets of refuge. For ecosystems on the brink, like coral reefs, scientists are exploring more radical interventions under the banner of assisted evolution. This isn't about creating GMOs, but about accelerating natural processes. They are stress-testing corals to build resilience, crossbreeding corals from warmer regions with those in cooler areas to spread heat-tolerant genes, and even creating hybrids of different coral species that show better survival rates. These are last-ditch efforts, designed to buy us precious time while the world gets its emissions under control. The ocean's acid test is really a test for us. The chemical changes we've unleashed are pushing entire ecosystems towards a tipping point, threatening global biodiversity, food security for billions of people, and coastal economies. While some marine life shows an incredible ability to adapt, for many, the pace of change is simply too fast. The future ocean risks becoming a simpler, less productive, and less resilient place. We cannot simply stand by and hope life finds a way. The silent dissolution happening in our oceans requires a loud, clear, and immediate response from humanity. It's a call to action to protect the engine of our planet, for the sake of the life within it, and for our own.